Hello everyone. We'll start with question number 3 of exercise 5.5. As you all can see it, this is an expression where a function is having another function as its index. So this is of the form a function to its index another function. Now this is a function. It cannot be treated as a constant. So we cannot use the method that we had for the derivative of x to the index n. N happens to be a constant. This is not a constant. So we cannot apply the rule that we applied here. So the alternate that we have is to bring it down to the base. Now the expression that can bring this function to a base is logarithm. Hence, we'll apply logarithm on both sides. That is, taking log on both sides. Just a log operator is added on both sides. The left hand side will be read as log of y. On the other hand, right side will be log of the expression that you have. Now the advantage of this logarithm is this is read as log of a to the index b. Log of a, this happens to be a and that is b, which is nothing but b log a. So therefore this function now has changed its form. It now takes the form of f1 multiplied by f2. So the derivative of f1, f2, differentiating one function at that once and taking the other function as a constant. We'll follow that method to have the derivative of this. So the left hand side is logarithm of y. So the derivative of log of y is its first logarithm function's derivative, that's 1 on y. Then the derivative of y, it's dy on. This is another way of expressing dy on. We read it as y prime. On the right hand side, we have two functions, f1, that's cos x. So the derivative of cos x minus sin x. The next function that you have, that is f2, is a constant here. Then plus, now f1 will be treated as constant, so it's cos x multiplied by the derivative of log of. It's log. Log's derivative is 1 upon. The log of the quantity comes to the denominator. Then it's log of log x, that's the next function. So it happens to be 1 upon x log x. So finally the derivative dy on dx of the expression is this y goes to the right hand side, which can be written as the function form and the whole expression that you have. So that's how we differentiate a function which is in the form of function to the index function. Now here, the next question, that's the fourth question. This is again in the form of fx is equal to x to the index x minus 2 to the index sin x. When you read it carefully, you'll be reading it as a function as f1 minus f2. It's read as f1 minus f2. Hence the derivative of it says it's the difference between the derivatives. So when you see the derivatives, we have the derivative of x to the index x minus 2 to the index sin x derivative. Now the problem is again x to the index x. X to the index x takes again the same form, log to the index cos, which is function to the index function, which says that this function that we have has to be brought down. So that is possible only with the help of logarithm. Now the problem here is in this expression, only this expression, that is f1 function, we need to take up separately to bring this x to the base. So the logarithm of this has to be taken. But unfortunately, logarithm does not have a property saying log of a minus b as log of a minus log of b. which says that we cannot apply logarithm individually on this expression. Hence, we will not be taking logarithm of the expression. Instead, we'll be going in for two different variables. We'll consider this as a variable u and this as another variable v. So this is read as, now the function is read as fx is equal to u minus v. So now u x to the index x, u x to the index x will follow the same property, have log on both sides. That brings this x of the index to the base. Hence this expression on the right hand side happens to be f1, f2, and the left hand side is a composite function log of u, derivative of it 1 upon u du on dx, the derivative of f1, f2, derivative of log x 1 upon x plus derivative of x, that is 1 multiplied by log x, which finally takes this form. Now coming to the next term, that is v. V is equal to 2 to the index sine x. 2 to the index sine x is nothing but the derivative of a to the index x. A to the index x, a is a constant, its derivative is a to the index x log a. So we can straight away apply the formula for a to the index x. So it happens to be 2 to the index sine x log 2 multiplied by the derivative of sine x, which is cos x. And the two together should be taken up. And finally, we'll have the derivative of the expression as du on dx minus dv on dx. Put the value here, you get the derivative of the function. There is one alternate way, that is sorry, we have exponential and logarithm as inverse of one another. So e to the index log of fx or log of e to the index fx, that's fx. So instead of logarithm, what I prefer is to rewrite the expression in terms of e. Wherever we come across to the expression x to the index fx, we take logarithm and exponential. This gives rise to this expression because log of a to the index b is b log a. So this is nothing but e to the index function. Hence, we differentiate e function. E's derivative is e itself. So this is e to the index, that is this whole expression, which is actually rewritten form of x to the index for x. So we write this as x to the index x. Now we differentiate this function x log x as usual by product rule. And then this is written as the derivative. So in one line, we can straight away write the derivative of the expression. That is using the formula of introducing exponential and logarithm. So all big expressions can be treated that way. Question number 6. We can read this as u plus v. Take up u. U is again fx to the index x. So we can write it as log. We can take log on both sides. Go in for the derivative of the expressions. A little bigger expression, so you'll have to be very careful in handling it. We again will have to take log on both sides to bring the function, this function to the base, and then finally sum it up. The alternate method. With the alternate method, we find that expression can be differentiated in one step. I have written e as well as log the function. Here, the index of this logarithmic expression, x, comes to the base of it, which is again the index of e. Doesn't matter. The index of logarithmic function comes as the base of the expression, which is again the index of that. Doesn't matter. So to differentiate this, we'll read it as e first. So it's derivative of e. Derivative of e is the same expression. So we copy the expression that we had, that is x to the index x plus 1 upon x to the index x, and then go in for the derivative of this function as f1 and f2's derivative. plus a similar term exponential derivative. So that expression is there with the derivative of 1 plus 1 upon x as f1 with log x as a constant, and then 1 plus 1 upon x as constant, log x derivative. That has been simplified. So it's your choice whether you need to go in for this alternate method, or you can take up expressions u and v and have the derivative. So this is how I have solved the rest of the questions of this exercise. So if you have any other doubt related to, go through all the solved examples and check whether you can manage to do it. For the 12th question again you'll find that x to the index y plus y to the index x is equal to 1. Exponential form would have been better, because otherwise you'll have to have this as u plus v, which will take a longer time. So you can cut short it by making use of exponential and logarithmic function.